Okay, in today's lecture, we're going to review the section 4.1 material on basics of differential equations. Now, we had started this material briefly before our spring break, but since it's been a couple of weeks since we've looked at this material, I thought it would be best to start over from the beginning to review some of the early stuff. So as a review, recall that we were working in Chapter 4 with an introduction to differential equations. And in this first section, 4.1, we're just going to discuss some of the basics. So let's recall, what is a differential equation? A differential equation is any equation that involves some unknown function and its derivative or derivatives. So any equation involving the derivative or derivatives of an unknown function is called a differential equation. And what we're trying to do for a differential equation is find the unknown function or functions which would satisfy that equation. So any function which would satisfy our equation is said to be a solution of that differential equation. So our solutions are always going to be functions. So in this chapter, one thing which is kind of nice to be able to do is, let's say that we think we've found a function which we suspect is a solution of a differential equation. Can we verify that it is indeed a solution? So in our first couple of examples, we'll look at problems like this, where in later sections of this chapter, you can check whether your function is indeed a solution of a given equation. So in this first example, we're asked to verify that the given function y is a solution of the differential equation y prime is equal to x minus y. So we want to substitute this function and its derivative or derivatives into our equation. And we can see by looking at our equation that it involves the first derivative. So my first step here is going to be to find y prime. So first, finding the derivative of our given function, we have, using the chain rule, negative 2 e to the negative x plus 1. And then we're going to substitute this function and our derivative into the equation. So what we're trying to see is whether y prime is equal to x minus y. We want to see if this function does indeed satisfy that equation. Now, on our left-hand side, we have y prime, which we just found to be negative 2 e to the negative x plus 1. And the question is whether or not that equals x minus y. Now, y in the problem statement is given as 2 e to the negative x plus x minus 1. So on our left-hand side, we have negative 2 e to the negative x plus 1. And we're asking whether that is equal to this right-hand side. So if we look at our right-hand side, we can simplify a little bit. We see that this x minus x will cancel, and we are left with a negative 2 e to the negative x minus a negative 1 or plus 1, and we see that this equation is indeed satisfied. So what that means is that the function we were given, y, which was 2 e to the negative x plus x minus 1, is a solution of our given differential equation. Now, in our next example, we'll see that a differential equation may have more than one solution. So in this second example that we're going to consider, we are given two functions, y1 and y2, and we are asked to verify that these are both solutions of the differential equation shown here. Now, when we look at this equation, we see it involves both the first and second derivatives of the function y. So for each of these functions I'm given, I need to calculate y prime and y double prime. So let's start by looking at our first function, y1. which is e to the negative 3t. So y1 prime would then be negative 3 e to the negative 3t, and y1 double prime would be a positive 9 e to the negative 3t by applying the chain rule. So if we think about plugging this into our differential equation, we're looking at y1 double prime plus 2 times y1 prime minus 3 times y1. We want to see if this will give us 0, if it will satisfy our equation. So we found here that y1 double prime was 9 e to the negative 3t. And then we have plus 2 times y1 prime. Now we found y1 prime was negative 3 e to the negative 3t. So multiplying by 2, we're left with negative 6 e to the negative 3t. And then minus 3 times y1, which was e to the negative 3t. And we see that adding or combining these terms on our right-hand side of the equation, we are indeed left with 0. So y1 will be a solution. Now let's check whether y2 e to the t would also be a solution of this equation. So here, if y2 is equal to e to the t, then we find y2 prime and y2 double prime are both equal to e to the t. Both my first and second derivative are e to the t. So substituting these expressions into our differential equation, we're looking at y2 double prime plus 2 times y2 prime minus 3 times y2, which gives us e to the t plus 2 e to the t minus 3 times e to the t, which does indeed give us 0. So we have found here that both y1, which was e to the negative 3t, and y2, which was e to the t, are solutions of our given differential equation. So it's often useful to check whether the function which you found is indeed a solution of the differential equation we started with. And this is how it can be done, as in these last two examples. So in our next part of this section, we will look at how we can possibly find these functions which might be a solution to a given differential equation. And one technique is by making an assumption about the form of our solution. So to illustrate this process, let's look at a couple of examples. In this next example, we are asked to find the values of r such that the differential equation shown here will have a solution of the form e to the rt. So we are assuming that our solution will be an exponential function, something of the form e to the rt, where r is a constant, and we want to find the values of r which would make that sort of function a solution of our equation. Now looking at this equation, it involves my first three derivatives of the function y. So our first step, as with the previous examples, is to find our first three derivatives. So here, if we are assuming that our solution has the form y equals e to the rt, then let's find our derivatives. Y prime, using the chain rule, would be r e to the rt. Y double prime is then r squared e to the rt, and y triple prime would be r cubed e to the rt. So now looking at our differential equation, we're supposed to make sure that y triple prime minus 3y double prime plus 2 times y prime is equal to 0. So let's see what we get when we substitute these expressions in. We found y triple prime to be r cubed e to the rt minus 3 times y double prime, which is r squared e to the rt, and then plus 2 times y prime, which was r e to the rt. We need to make sure that this is equal to 0 in order to satisfy our equation. So on this left-hand side of our equation, we can now try to solve for r. And we see that from this left-hand side, we can factor out an e to the rt, and we're left with r cubed minus 3r squared plus 2r is equal to 0. Now, our lead term, e to the rt, we know can never equal to 0. The range of exponential functions is the set of positive real numbers, so if this lead term can never be 0, that means that the expression in parentheses, r cubed minus 3r squared plus 2r, would have to equal 0 to satisfy this equation. So now from this polynomial, we can factor out an r, and we're left with r squared minus 3r plus 2 is equal to 0, and then that quadratic can be factored as r minus 1 times r minus 2. So in order for the product of these three factors to be 0, that means one factor must be 0. So one of our options would be to have r equal to 0. Another option is r equals 1 to make our middle factor 0, or r equals 2 to make that third factor 0. So these are the three values of r, such that our solution would be of the form e to the rt. So by plugging these values of r into the general form of our solution, y equals e to the rt, well, if r is 0, we have e to the 0, which would be 1. We could have e to the 1 times t, or e to the 2 times t, and these would all be solutions of that differential equation. So we're seeing that a given differential equation might have more than one solution. Now in our next example, we have a very similar problem. We are asked to find the values of some constant r such that the given differential equation would have a solution of the form t to the r power, where t is some positive variable. So again, looking at our differential equation, we see it involves y and our first two derivatives. So our first step here is going to be to find the first and second derivatives of this function. So if our function is of the form t to the r power, then we find our first derivative, y prime, using the power rule, would be r times t to the r minus 1 power. And then our second derivative, y double prime, is r times r minus 1 times t to the r minus 2 power. So we're now going to take these expressions for our derivatives and substitute them into the given equation, which was t squared times y double prime, which is r times r minus 1 times t to the r minus 2. Then minus 4 times t times y prime, which was r times t to the r minus 1 power, and then plus 4 times y, which was t to the r power. And we need this to equal 0 in order to be a solution of the given equation. So now the expression that we're left with on the left-hand side isn't quite as simple as what we had in that previous example, so we need to start by simplifying some terms. So if we look at this first term, we have a t squared times t to the r minus 2 power. So if we're multiplying these power functions with the same base, we would add our exponents, and we're left with r times r minus 1 times t to the r power. When we combine those power functions, t squared and t to the r minus 2, when we add those exponents, we just have t to the r. Now, in a similar way, in this second term, we have a t to the first times t to the r minus 1. So when we combine those terms, we just get t to the r, and we're left with negative 4r times t to the r power. And then our last term is simply 4 times t to the r, and we need this to be 0 to give us a solution. So now, if we look at the expression on this left-hand side of our equation, we notice that every term involves the factor t to the r power. So if we factor out t to the r power, we are left with r times r minus 1, or if we distribute the r squared minus r, minus 4r plus 4 is equal to 0. Now, as with our previous example, this lead term which we factored out, t to the r, can never be equal to 0 here. And the reason being is that we had assumed t was positive. So if I take a positive number and raise it to some power r, it's going to be positive. We could never have a 0 value. So the only way for this equation to equal 0 is if the part in brackets here, which reduces to r squared minus 5r plus 4, is equal to 0. And this quadratic can now be factored as r minus 1 times r minus 4 equals 0. And so we're left with r equals 1 or r equals 4. So these are the values of r that we were interested in. And again, if we were to take these values for r and substitute them into the general form of our solution, which was t to the r, we would have two different solutions. Y could either be t to the first power or t to the fourth power. These would both be solutions to that given differential equation. All right. Now, in the next part of this section, we will review the classification of differential equations. So in order to determine how we might solve a given equation, it's often useful to classify it. And based on the type of equation that we're working with, we'll have different methods for finding solutions. Now, there's many different classifications for differential equations. In our course, we will only discuss two, namely the order of a differential equation and its linearity. So let's review the concept of order. We would say the order of a differential equation is the order of the highest derivative that appears in that equation. So if we had an equation involving up through the second derivative, that would be a second order differential equation. If we had a differential equation that involved up through the first, say, 5 derivatives, it would be a fifth order equation, and so on. Now, what's a little bit trickier to define is the concept of linearity. So let's define linearity. We would say that a differential equation is called linear if it can be expressed as a linear combination of my unknown function. Typically, we use y to denote that function, and its derivatives. So in general, a differential equation is said to be linear if it can be expressed in the following general form. So say, for instance, we would start with our original unknown function y, and I could be multiplying that function y out in front by some function of t, a sub n of t. And then we could move to, say, our next derivative, say the first derivative, y prime, and I could be multiplying this function y prime out in front by a function of t, say a sub n minus 1 of t. And then I could have another term involving, say, the second derivative and the third derivative and so on, up until we have our n minus first derivative or the nth derivative of our function y. And if our equation can be expressed in this form, then our equation is said to be linear. Otherwise, our differential equation is called nonlinear. So what we're really looking at here to determine linearity is that we don't have any nonlinear functions in terms of y or its derivative. So that is nothing involving y squared, sine of y, e to the y, 1 over y, anything that would be a nonlinear function of y or the derivatives of y would be considered nonlinear. So as some examples of classifying differential equations, let's look at the following. So in this next problem, we're given a differential equation, and we are asked to classify it as to its order and linearity. So in this first example, part A, we will start with the easy classification of order, and we see that our differential equation involves y prime, and y double prime, which is the highest derivative that appears. So the second derivative was the highest derivative, which means that our differential equation would be second order. Now, to address linearity, we would see whether this equation has the general form that we discussed earlier. So if we look at our lower terms, well, we have a 1 times y, a function of t, namely t times the first derivative y prime, and then for this first term, well, we had a y double prime, but out in front, we did not have a function of t. We have a 1 plus y squared, and this y squared term is quadratic with respect to y. It is not linear. Therefore, our differential equation is nonlinear. So here we have a second order nonlinear equation. Now in part B, we could start by addressing order first. And when we look at our differential equation, we see it involves up through my third derivative and no higher order derivatives. Therefore, our equation is a third order differential equation. And to address linearity, again, we want to see if it has the general form of a linear equation that we were discussing previously. So starting with our original function y, well, we have y to the first power, and it's being multiplied out in front by a function of t, cosine squared of t. Now this cosine squared function is nonlinear, but remember, for linearity, we only need our differential equation to be linear with respect to y and the derivative. So I don't care about this function of t being nonlinear as long as I don't have any nonlinear terms involving y or the derivatives. So moving to our next highest order derivative, we have a y prime times a function of t out in front, still has the general form that we're after. And then for this higher order term, we have a 1 times y triple prime. And it's equal to t cubed. So when we were talking about our general form, this right-hand side can be any function of t. So we see that this equation does indeed have the general form of a linear equation. So it is a linear differential equation. Now in part C, let's again address the order of our differential equation. We see that our equation only involves the first derivative, dy dx, which is the Leibniz notation for the derivative of y with respect to x. And so since our equation only involves the first derivative, this is a first order differential equation. And to address linearity, Well, we can see if this equation has the general form of a linear equation. And we can see, looking at this first term, we have an exponential function of y, which is not linear. So here, this exponential function of y implies that we have a nonlinear equation. It does not satisfy that general form. Therefore, our differential equation is nonlinear. Now, in our last part of this example, part D, let's start by classifying our order. So we see that we have a y double prime, and then there's this y with a superscript of 4, but in parentheses. So recall that this is notation for the fourth derivative of our function. So since our differential equation involves the fourth derivative, and that is the highest order derivative which appears, this would be a fourth order differential equation. And then to address linearity, we would again see if this has the same general form of a linear equation. So looking at our second derivative term, we have a y double prime, and there's a function of x out in front, negative 6x. Now, in the general form that we had discussed, we said we had a function of t out in front, so y could be considered as a function of t, or in this case, y might be a function of x, so we really don't care whether that variable is t or x or any other variable, as long as our equation is linear in terms of y and the derivatives. Now, if we move to that fourth order derivative term, we again have a function of x out in front, 1 over x, which is nonlinear, but we only need linearity with respect to y and the derivatives. And then on our right-hand side, we have log of x, which is just a general function of x. So this does indeed have the form of a linear equation. So this is a fourth order linear differential equation. So a little practice here with reviewing whether an equation is linear or not and determining its order. Now, in the next part of this section, we will discuss how to find solutions of one type of differential equation and discuss something called an initial value problem, or finding general or particular solutions of a differential equation. So in this next example, we are asked to consider the differential equation y prime is equal to the following function of x. So we're given the derivative y prime in terms of the variable x alone. So if we're looking for the solution of this differential equation, that is the function y, which satisfies this equation, all we would need to do is find the antiderivative of the derivative that we're given. So if we know the derivative y prime, taking the antiderivative of that derivative would give us our original function, y, which would be our solution. So in the first part of this example, we are asked to find what is called the general solution of this differential equation. And to do that, we're going to, as we said, take the antiderivative of the derivative of our function, which was given as sine of x plus 4x plus e to the x. And this is a function of x, so we're integrating with respect to x. And we find that y, or sometimes we might write y of x, since it is a function of x, is equal to, well, let's find our antiderivative. Antiderivative of sine of x is negative cosine of x, plus antiderivative of 4x is 2x squared, and the antiderivative of e to the x is e to the x. Now this is an indefinite integral, so we know that we could write any general constant, c, on the end, and it would still be an antiderivative. So what we found here is a function y of x, which would be a solution of our differential equation, and it depends on this arbitrary constant or general constant c. Now, this is the reason that we would call such a solution a general solution, because regardless of what the value of this constant c is, we could take it as 0, 1, -50, pi, and we would still have a solution no matter what I chose as that constant. So what we're seeing here is that this differential equation has infinitely many solutions because there are infinitely many choices for this constant c. Now, if we think about graphing our general solution for different constant c, we get a geometric representation of our solutions as a family of curves, which are called integral curves. So let's think about graphing the general solution that we just found for different values of the constant c. So here our general solution was pretty messy, but if we think about graphing this in general, well, let's maybe start by graphing by looking at a specific x value. So if we chose, say, x as 0, we would have our function would be negative cosine of 0, or -1, plus 0 plus e to the 0, which is 1 plus my constant. So when x is 0, I have y of x, or y of 0, is whatever my constant c is. And this last term in our solution, e to the x, dominates the growth of our function. So in general, this solution will pass through 0c, and as x gets large, it looks something like exponential growth. Now, for small values of x, we aren't quite sure what's happening with our function here without doing a little more work. So this first curve, maybe passing through the y-intercept 1, would be corresponding to the value c equals 1. If c were equal to 0, then the value of our function at 0 would be 0. Our curve would pass through the origin. And we see that for different values of c, we would have the exact same function either shifted upward or downward by the factor of c. So we get this collection of curves, which are called integral curves, for our differential equation. Now in the second part of this example, part B, we are asked to find the particular solution which passes through the point 0, 6. So we're looking for the specific function whose integral curve, or whose graph, would pass through the point 0, 6. So this point, 0, 6, gives us some condition on x and y that must be satisfied for our general solution. So if we look back at what we found in part A, let's recall that y of x in general had the form negative cosine of x plus 2x squared plus e to the x plus some constant c. And we know that our curve must pass through the point 0, 6. So what that means is if x is 0, if I plug in 0 for x, I should be getting 6 as the value of my function. So let's see what we have when we plug in 0. We get a -1 plus 0 plus 1 plus c, which has to equal 6. So we find, after simplifying, that the constant c must equal 6. And then we can take this value for our constant and substitute it back into the general form of our solution. And we find that y of x is the negative cosine of x plus 2x squared plus e to the x plus our constant c, which in order to pass through the point 0, 6, had to be 6. So this would be the particular function which passes through that point 0, 6. So this sort of solution is sometimes called a particular solution of our differential equation. Now, this condition that we were using to find our particular solution is called an initial condition. So the condition that we were given that our curve had to pass through the point 0, 6 is what is called an initial condition. So if we think about the problem that we were solving in this last example, where we found a general solution of a differential equation, and we also made sure it solved or satisfied some initial condition, this sort of problem is what is called an initial value problem. Any problem where we are asked to find the solution of a differential equation that also satisfies some initial condition, say passing through a given point, is called an initial value problem. So in our next examples, we will get a little more practice with solving these initial value problems. So in this next one, we are given the differential equation y prime is equal to this function of x, and we are given an initial condition y of 0 equals 8. Okay, so here we're finding that our curve has to pass through the point 0, 8. When x is 0, y must be 8, and this is what is called our initial condition. So as in our previous example, to find a general solution of this equation, we would let y be the antiderivative of the derivative, which was given as x squared minus 4x plus 3 minus 6e to the x, integrating with respect to x. So we find here that y, or y as a function of x, is 1/3 x cubed minus 2x squared plus 3x minus 6e to the x plus some constant c. So this that we have found so far is, again, what's called a general solution, because it depends on this general constant c. Now, in order to solve our initial value problem, we have to also make sure that our initial condition is satisfied. So applying this initial condition, we saw that when x is equal to 0, y has to be 8. So let's see what we get when we plug in 0 for x in our general solution. So all that we're left with is a -6 times e to the 0, or 1, so -6 altogether, plus a constant c, and we're told that this has to equal 8. So solving for the constant c, we're left with 14, and then we would take that value that we found for our constant and plug it back into our general solution. So here we find that y, or y as a function of x, is 1/3 x cubed minus 2x squared plus 3x minus 6e to the x plus 14. And this would be the particular solution of this initial value problem. So very similar to what we saw in that last example. So in our next example, we have a similar problem. We were asked to solve the following initial value problem where y prime is a given function of t, and our initial condition is y of 0 equals 5. So this means that our curve, the graph of our solution, must pass through the point 0, 5. So to solve this initial value problem, we're going to start by finding our general solution. And to find our general solution for y, we're going to let y be the antiderivative of our derivative, which was given as 2t times the square root of t squared plus 4. Here, y is given in terms of t, so we're integrating with respect to t. And we see that to find the antiderivative of this function, we're going to need a u substitution. So our integral involves a composite function, the square root of t squared plus 4. So to integrate this, we might make use of a substitution where u is this inside function, t squared plus 4. So that du is equal to 2t times dt. So now rewriting our integral in terms of u, we have y is the integral of the square root of u, and then our 2t times dt is exactly equal to du. So we're just left with the square root of u times du. And the antiderivative of this is then 2/3 u to the 3/2 power plus some constant c, or substituting u back in, we find that y, which is a function of t, is 2/3 times u, which was t squared plus 4, all raised to the 3/2 power plus some constant c. So here, again, we have found our general solution, but we still need to solve for the constant c to make sure that our initial condition is satisfied. So here, let's look at our initial condition. We saw that when t was 0, I had written x up here, as this is a point ty. When t is equal to 0, we have 2/3 times 4 to the 3/2 power, or 4 times the square root of 4, which leaves us with 8, plus our constant c, and we were told that this had to equal 5. So simplifying a little bit, we have 16/3 plus c is equal to 5, or 15/3. So c is then negative 1/3. And taking this constant c and substituting back into our general solution, we find that y of t is given by 2/3 times t squared plus 4 to the 3/2 power plus c, which is minus 1/3. So this expression would be our particular solution of this initial value problem. Okay. So in the last part of this section, we will start talking about some applications of differential equations. And there are many applications in general for differential equations. We will discuss some simple ones in our course, and these applications will be in mathematical modeling. So let's describe, well, what exactly is a mathematical model? And typically, a mathematical model involves differential equations. So any differential equation which describes some physical process is called a mathematical model of that process. So examples of physical processes which we might model are, say, a falling body problem, like if we threw a rock into the air. We'll see a little bit later in this chapter examples in describing population growth. There's a bunch of examples in infectious disease dynamics, and the rate of change of an infection through a population, which is of important interest right now. So there's a lot of different models that we could consider, and in this section we'll consider a pretty easy model describing a falling body. So in this first example, we are given some rock with a mass of 0.1 kilograms is thrown upward from a height of 3 meters above the Earth's surface with an initial velocity of 10 meters per second. And the only force acting on this object is the force due to gravity. So here gravity is really an acceleration, not a force. And we are asked here to find the position of our rock after t seconds. So let's think about what we could do to find our position. What we are given here is the only force or the only acceleration acting on our rock is due to gravity. So we know here that the acceleration of our object, this rock, at any time t is going to be the acceleration due to gravity, which we typically denote as lowercase g. And gravity is acting in a downward direction on our rock. So typically we would use the convention that this acceleration would be considered negative since it is acting in a downward direction, and we'd use the convention that a positive value would be an upward acting force on our object. So here the acceleration due to gravity is acting downward, so we have a negative g. And the value that we're going to use for gravity here, since we were measuring everything in meters or meters per second, is going to be a 9.8 meters per second squared. So what we have is the acceleration of our rock at any time t, and we are asked about its position, information about its height above the Earth's surface. Now we know that acceleration is the derivative of velocity, and velocity is the derivative of position. So what we're given is the second derivative of our position function. Acceleration would be the second derivative of our height. So we need to work backwards from acceleration to find our position. So our first step, since we know acceleration a of t would be the derivative of velocity. So velocity, if we call it v of t, this acceleration would be v prime. So to get v of t, the velocity, well, we would take the antiderivative of the derivative, a of t, which was negative 9.8 meters per second squared, integrating with respect to t here. And we find that our antiderivative is then negative 9.8 times t plus some constant. I'm going to call it c1. And we need to solve for this constant c1. So what we found so far is the general form for our velocity function, but we need c1, which means that we need some initial condition about velocity. Now, if we read back through the problem statement, we are told that the initial velocity of our rock is 10 meters per second, and this rock was being thrown upward. So that would correspond to a positive 10 meters per second, since it's acting in the upward direction for our velocity. So what we're given is the velocity of our rock at time 0, at the moment that this rock was being thrown. Now, if we plug 0 in for t, in the general solution that we just found, we are just left with c1, and we know that this has to equal a positive 10 meters per second. So taking that constant 10 for c1 and substituting back into the general form for velocity, we find that v of t is equal to negative 9.8 t plus 10, where velocity is being measured in meters per second. Now, we were asked about the position or the height of our rock after t seconds, and we know that the velocity of our object is given by the derivative of the position or the height, which I'll call h of t. So the derivative of our height is velocity. So to find height, h, at any time t, we would integrate the derivative of height, which is our velocity function, negative 9.8 t plus 10, integrating with respect to t. And we find that h of t, our height or position, is then negative 9.8 times t squared over 2. So here, half of 9.8 is 4.9 t squared, plus 10 times t plus some constant c2. And again, we need to solve for this constant c2, which means that we need some initial condition on our height or the position of our object. So again, looking back at the problem statement, we are told that this rock was thrown upward from a height of 3 meters above the Earth's surface. So our initial condition on height is 3. So let's apply this initial condition. The height of our rock at time 0, that is the moment that it was thrown, is equal to 3. And if we plug in 0 for t in the general form that we found for our height function, we're just left with c2, which we know has to be 3 meters. So finally, we find our position or height function, h of t, is negative 4.9 t squared plus 10 times t plus c2, which is 3. We're measuring height in meters here. So this would be the position of our object, which is this rock, t seconds after it was thrown. Now, once we have these functions for the position, the height, the velocity, acceleration of our rock, we can answer different questions about the motion of this rock over time. So in part B of this example, we are asked with what velocity does the rock hit the ground? Now, in the previous part of this example, from part A, we had found that the velocity function, v of t, was negative, let's look back at it, 9.8 t plus 10, where we're measuring in meters per second. So we have the velocity of our rock at any given time, and we're asked about the velocity when the rock hits the ground. So we need to first determine the time at which our rock hits the ground. Now, in order to determine that time, when our rock hits the ground, well, that means it must be at ground level. So the height of our function, h of t, or our position function, must be 0. So let's see what we get if we set our position function, or our height function, which in part A we found to be negative 4.9 t squared plus 10t plus 3. If we set this equal to 0, we need to solve for t to determine when this rock hits the ground. So here we're left with a quadratic in terms of the variable t, and we're trying to find where that quadratic is 0. So in order to solve a quadratic, we could try factoring, but in this example, it doesn't seem like this is going to factor very nicely. Or if it doesn't factor, we can always make use of the quadratic formula, which says that the roots of our quadratic t would be given by negative b. So in this case, our value for b was 10, so negative 10, plus or minus the square root of b squared. So here we would have 10 squared, or 100, minus 4 times a, which is negative 4.9, times c, which is 3. And then all over 2 times a. So we have 2 times negative 4.9. So we have two different values of t for this quadratic, one corresponding to the positive square root, one corresponding to the negative square root. So let's simplify this expression a little. We have negative 10 plus or minus the square root of 100, and then our negatives here will cancel. We're left with 4 times 3, or 12, times 4.9, all over this 2 times negative 4.9, or negative 9.8 on bottom. Now, we're curious about which of these values of t that we want, the one corresponding to the positive square root or the one corresponding to the negative square root. And in order for this value of time to make sense physically, it better be positive. We were letting 0 for t denote the time at which we threw our rock, so the time at which it hits the ground would have to be a positive value of time, sometime after we had thrown the rock. And in order for this value of t to be positive, since we are dividing by a negative 9.8, we need our numerator to be negative. So we're going to take the value of t corresponding to this negative 10 minus the square root, so that we would have a positive time. So t would be negative 10 minus the square root of 100 plus 12 times 4.9, all over negative 9.8, which if we cancel all our negatives, or say multiply top and bottom through by negative 1, we have positive 10 plus the square root divided by positive 9.8. So this is now a positive value of time which our rock hits the ground. Now the question asked, what is the velocity of the rock when we hit the ground? So we're going to take this value that we just found for time and change colors here. Substitute it into our velocity function. So we find that the velocity, v, at this time that we just found, 10 plus square root of 100 plus 12 times 4.9, all over 9.8, is equal to, well, let's see what we get. We have a negative 9.8 times t, which is given by 10 plus the square root of 100 plus 12 times 4.9, all over 9.8, plus 10. So here this looks a little messy initially, but it simplifies pretty well. We see that our 9.8 in the numerator and denominator here will cancel, and so we are left with a negative 10 minus the square root of 100 plus 12 times 4.9. So we distribute that negative that we had out in front, and then we're adding 10. So from here, our negative 10 and positive 10 will cancel, and we're left with the negative square root of 100 plus 12 times 4.9. So whatever value that works out to without a calculator, it's a little tough to approximate. So here we would have the velocity of our rock at the time that it hits the ground as negative, the square root of this value measured in meters per second. So we might ask, well, what's with the negative value out in front? So when our rock hits the ground, it is moving downward. Since we initially had thrown it upward, it has to come back down. So the negative out in front here denotes the fact that our rock is moving downward rather than upward at the time that it hits the ground. So that finishes up our section 4.1 material on some basics of differential equations. If you have questions on any of this material, feel free to contact me through email or virtual office hours to ask some questions about this.